Hey, pre-calc students, this is Mr. Beck. How are you doing? I wanted to talk to you today a little bit about quadratic models. We're going to be building those quadratic models and then working with quadratic inequalities. Just a quick recap of some of the things that we've done over the past. In chapter 1, we talked about a lot of individual skills, distance formula, midpoint, intercepts. We talked about lines at that point too. Then in chapter 2, we talked about functions. With those functions, we had function notation, we talked about increasing, decreasing, and from that came relative extrema as well. And then at the end of chapter 2, we talked about building models of functions, and we use technology to evaluate those absolute extrema. What we're going to do today is we're going to utilize some of those aspects along with what we did in chapter 3, which is linear and quadratic equations. We're going to combine that all into one distinct idea. That we're going to be building quadratic models today, and then we're going to understand what's going on with those quadratic models, such as the absolute extrema on a quadratic are going to be, in new terminology, optimizing. So the optimizing optimum value, the minimum value, or the maximum value can be based on whether your quadratic opens up or down. If your quadratic opens up, we have an absolute min, and if your quadratic opens down, we have an absolute max. And so we know that by our leading coefficient. So a lot of times we're going to be asking for what's the maximum revenue, what's going to be the maximum profit maybe. I'm trying to think of some of the other examples in today's notes. We have both, we talk about revenue. So with that, chapter 3 had a very distinct business flavor, as we have talked about. And one of the big ideas is revenue is price times quantity. Variables we tend to use in this book are prices, capital, or prices P, and quantity is X. Now, with that said, we have our first problem that says we have demand of a certain type of calculators given by this expression. Now, in 3.3, actually, I guess it's 3.1, we call this D of P. So we call this D of P. Now, D of P was really replacing the idea of X, where X is the quantity. So D of P is X, and D of P is 21,000 minus 150P. And what we're doing is we're writing a model that expresses revenue as a function of price. And then our goal is to find that maximum revenue. So to begin, I know I have a demand, which is our quantity. And so I'm going to start off with, and let me go to highlighter mode. R equals P times X, meaning revenue is price times quantity. Our price, we want everything in terms of P. So we want revenue as a function of price. So R of P, and let me go ahead and write that. I'm not sure why I didn't have that before. So R of P is going to equal P times 21,000 minus 150P. So with that said, we have an option of saying, okay, let's take it to standard form, and then we could figure out where we have the maximum revenue. So the price that we'll get our maximum revenue, we could do negative B over 2A, which is what we're seeing right here. And if we do that, then we get 70. Now, an alternate approach, and something that I see a lot happen in this section, is we can, rather than put it in standard form, let's utilize the intercept form. So that involves factoring. So if I factor out the negative 150 from here, what we can see is this is our intercept form, and halfway between the intercept, so halfway in between, is P equals 70. So halfway between. So either way we get it, $70 is going to be the price that gives us the maximum revenue, and that maximum revenue is $735,000. So on to problem number 2. Parabolic arch has a span of 120 feet. And what we're doing with this parabolic arch is we're looking at the maximum height of it is 125. So what I did with this was I kind of drew out my situation. So let's draw out the situation. We have a parabolic arch. We know that the span is 120, so I have that labeled down here. And we know that the maximum height is 125. That would be my vertex. Now, from that, I developed where do I really want to put my axes. It's possible for you to put your axes that look like this, and so you have your vertex at 60, 25. You can see where I put the axes. If you really wanted to, you can have your vertex at 0, 0, and establish a coordinate system that way. I think that's probably the worst of the 3 options of what I presented, but it doesn't really matter which option. You're just creating a series of points. So once you've built your model, or sorry, once you built like what it looks like and you establish where the coordinates are, then all we do is kind of what we did last time. So I'm starting off with vertex form mainly because I was given the vertex, knowing that the height is 25 feet. And really, I kind of built the axes where they are, so it's more of in vertex form anyway. So we fill in the h is 0, the k is 25. And then that's where we use our another point. The other point that I have is using the span of 120 feet, which creates this coordinate here, 60, 0. Then I could fill it in, solve for A, just like we did last time. That's why it's more of a level 2 problem, because we've seen it before, we've worked with it before, we're just putting it in terms of a context. In the end, I do have to figure out my A value. My A value is -1 over 144. And then one more step, and I'm trying to change colors here. I think I'm just going to go back to the green. We're going to calculate the height 40 points or 40 feet from the center. So that's what I'm doing here. I have that point 40 feet from the center. I plug in 40, basically I'm finding f of 40, and I get 13.889. Really it's 13.8 repeating, but 13.889. On to the next problem. And then this problem is definitely a lot more in depth, but what I'm hoping to show with this kind of problem is how all of this is interconnected and all this works together. So first thing, what is the implied domain of the demand quantity? So I guess let me restart. The price P is in dollars, the quantity X is sold of a certain product. Obey this demand equation. And remember, once again, this is R of P. So that's, or not R of P, D of P. That's our demand function. The D of P equals -20P plus 500. Now, what is the implied domain? So I'm not going to tell you demand is going to be negative when it comes to an assessment. That's something that I'm expecting that you know. So what is the implied domain? We set our demand equal to 0 and solve for P to get 25. So visually what's happening here is we know that we have a y-intercept of 500, and then the x-intercept is now 25. So our implied domain is from 0 to 25. Now, if we express the revenue as a function of P, once again, just like we did before, revenue is price times quantity. And then what I did was I immediately went to the intercept form. And one of the things you should notice when it comes to this intercept form, meaning I collected out the -20, is the intercepts also align with the domain or the implied domain. That's a very, very important idea. Now, what's happening with this revenue, if I graphed it, we know that this intercept is 0. We know this intercept is 25. And what we could do is we could say, okay, halfway in between, that's the price of $12.50. And then that really answers the question that we're asking here. And then how many units need to be sold to maximize the revenue? So we have a couple different options here. Right from the beginning, we are given this demand equation, which I highlighted, but we are given this demand equation up here. We can use that demand equation to say, okay, what is X of our price when we get 250 units? And then we can plug in 250 into our revenue function. Our revenue function we have back up here. So as I said, this is all interconnected. So we're going to have a series of different ideas all kind of working together. The R of $12.50 is 3,125. That's one approach we could have taken. Once we knew that we had 250 units, also, we could have said, hey, price times quantity, which also gives us $3,125. This is this part of the problem is where we get a little different. So where we get different is we need to express the revenue as a function of X. To express the revenue as a function of X, what I know is revenue is price times quantity. We have our demand in terms of price. So let's take our demand in terms of price and let's rewrite it. So our demand is in terms of quantity now. So this is now officially going to be D. I'm not sure why I keep putting R, it's not revenue. D of X is going to be 25 minus 120 of X. So as a result, if you remember in the video that I put in last time, I said price and quantity aren't really necessarily independent and dependent variables like what we're used to. Not really or dependent, independent, they're called codependent because sometimes we might have the demand in terms of price, sometimes we might have the demand in terms of quantity. If I'm a consumer, I pretty much am looking at price and saying, okay, everything that I do is based off of the price. Well, if you're a business, everything you're doing is probably going to be based in terms of the quantity because you want to know how many you're making. So both are legitimate. With both of those being legitimate, then it comes down to what is the situation, what do you need? In this case, I want to have my revenue in terms of quantity. So I'm kind of looking at this from the business side, revenue in terms of quantity. So I put my price in terms of quantity, like so, and price times X, and I now have this expression right here. So revenue of X. If I really wanted to, I could check what is R of 250 in that case, and what should end up happening is we get 3,125. So what I was just saying was, if I wanted to check what is R of 250, it should equal 3,125 also. Anyway, a company needs to maintain a revenue of at least $3,000. What price should the company charge? So what I'm kind of looking at in this situation is a graph like this. We have our revenue graph, and I wanted to have at least 3,000. So the approach I'm going to take is I want to know where my revenue is going to be above that, so, or at least so greater than or equal to. So in this entire region, what are those prices? To do that, I solved and I used the quadratic formula. So as you see here, I set my revenue greater than or equal to 3,000, brought everything to one side right here, and I divided by -20 to create this inequality. I did factor it, and notice how I flipped the sign. Then I did factor it P minus 15 and P minus 10. And that was important because once I was able to factor that, then I knew that my prices here on the graph are 10 and 15. One of the things that I'm going to do at the very end of today's lesson is kind of go back into how these inequalities work. So I'll talk more about that and show a more specific approach to it other than just looking at the graph. Next problem. I have a hobby of farming and decides I want to add sheep to my farm. So after buying my sheep, I have enough money to purchase 3,000 feet of fencing to build a rectangular pen. So anytime that I have something like this, I like to draw a picture so I know what's going on. This is my rectangular pen, and that pen has a length and a width. So my first question is express the area of the sheep pen as a function of x. I know area is length times width, but x represents the length. So I'm replacing my length with x. And then the width, I need to figure out what is my width in terms of x. To figure out what my width is in terms of x, let's go back to the rectangle that I drew and said, okay, this is x and this is my width. I know that my perimeter is a total of 3,000. So 3,000 is 2 lengths plus 2 widths. Solving it for w, I get 1,500 minus x. And that's what I put in up here for my area function. Now you are welcome to multiply it together, negative x squared plus 1,500x if you prefer. You could leave it in intercept form, which is kind of what I have here. You could write as negative x times x minus 1,500. So once again, when it comes to pre-calculus, you have a lot of freedom to do things in many, many different ways. So what value of x will enclose the largest area? The nice thing about having this problem in intercept form is I can graph it. I'd like to do a very, very quick visual graph. I could say, okay, if this is 0, this is 1,500. Halfway through is where we're going to have our largest area, and then plug it in. So A of 750 gives us 562,500 feet. Then after a few months, I noticed that some of my sheep have mad sheep disease. This is a completely made up thing, but anyway. So I have mad sheep disease, so I tear down the original fence and I build 2 rectangular enclosures sharing a common side. So basically, I put these 2 together and they have a common side. So what that does is that's going to change the dimensions of my pen. How does it change the dimensions of the pen? And what's the largest area that I can enclose? Well, now this is still x, which is the length of the whole thing. My width is going to be different. But as I said, my perimeter now has 3 widths instead of just 2 widths. There, because I'm including this middle piece also. So solving for w, I get 1,000 minus 2/3 x. So I put that into my area function, which I'm calling p, just as something different. So this is the intercept form. So once again, if I go and say what's halfway in between 0 and 1500 should be 750. Yes, you could do negative b over 2a or any of the other strategies. I like having the intercept form because halfway in between my intercepts of 0 and 1500 will give me the 750 again. And then P of 750 is 375,000, which will be my new largest area. So let's talk about some inequalities. We have two ways that we can solve quadratic inequalities. Let me actually start with the numerical first, because this is a little bit more appropriate, kind of like stemming from what was going on in Algebra 2. So if we have this quadratic, and I want to know where is this quadratic greater than or equal to 0, what I could do is I could find the zeros, and I could do that by factoring. Use the number line to plot my zeros, which is what I have here. So my number line to plot my zeros. Once I have my number line, then determine where the regions are positive or negative. So what's the idea behind here? If I plug in numbers, and this is where quadratics are continuous everywhere, so their domain is all real numbers. We've discussed this over time. So if our quadratics have a domain of all real numbers, all those numbers are going to yield positive numbers, negative numbers, or 0. So if I plug in an x, it's going to give me a plus, a minus, or a 0. We found the zeros by factoring. So these are my two zeros. Every other number is going to be positive or negative. And the only way that those numbers can change from positive to negative is to go through 0, which means everything in this region is either all positive or negative. Everything in this region is all positive or negative. Everything in this region is all positive or negative. So we could test number values. If I plug in -8 or -8, we'll get -2 times -10, which is a positive value. Now, hopefully you realize we really didn't need to plug in -8. We didn't have to like come up with -2 times -10. What we could have done is just said, what's the sign of what actually occurs as a result? So if I plug in 0, I will get a positive times a negative. So everything in this region is negative. If I plug in a 3, I will get a positive times a positive, which results in a positive. What this means is if I want all of my solutions are going to occur where I have positive regions, which would be from -infinity to -6, and then from 2 to infinity. So my solution set is -infinity to -6, bracket, and that bracket is because we're allowed to be equal to, then union to bracket 2 to infinity. So that is the more numerical and algebraic side at the same time. What we could do over here is we could take a look at this graphically and say, let's assume that this is more two-dimensional instead of one-dimensional. If this is two-dimensional, then we have a parabola which is going to cross the x-axis, in this case twice. Those two zeros are going to be the zeros that we found before. And then our parabola, this opens up. So we know that our parabola, as I said, opens up. And we want to know where all of the y values are positive. So what this graph represents right here, kind of numerically what's going on over here, where we could really just assume that there's a parabola there, and we can see that the values that come out model positive values, negative values, and so on. All right, so to solve this quadratic, what we do, and I'm just not zooming. Okay, so to solve the quadratic, let's go ahead, factor it. And I took the graphical approach on this one and said, okay, this has a positive leading coefficient. So I know this is going to go or open up through my zeros. And I want to know where my quadratic is just greater than 0. So that's going to be everything over here, which is -infinity to -4, or everything over here, which is -3 to infinity. On this one, we first have to get everything to one side. Once we get everything to one side, what I did was I factored this, and I factored it through the split the middle process. So I said, okay, what multiplies to give me -36, which are these two numbers multiplied out, and it adds to give me -5, and that is -9 and 4. So what I did was I split -5x into -9x and +4x. Factored out my GCF from these two terms, my GCF from these two terms, and then factored out the GCF from both of these two terms, and that GCF is 2x minus 3. Excuse me. So I have my two zeros, and then I look at the inequality to say, okay, my inequality, I want to know where this is less than 0. So if I drew a parabola, that parabola would be less than 0 between -2/3 and 3/2. On to this problem. I have a parabola and I have a line, and I want to know where is f of x less than g of x. So I can algebraically do this. I could plug in f, I could plug in g, bring everything to one side, factor, and I want to know where this is less than 0. So my mock parabola, again, this one opens up. It opens up because of the positive leading coefficient. I want to know where this is less than 0, which would be in this region, so from -3 to 2. Not including the endpoints, and that's because it's just less than, not equal. Graphically, if I graph both, what this actually says is, where is the parabola less than the line? So the parabola is less than the line on the region from -3 to 2. Last but not least, if we have an object thrown in the air, it will follow a parabolic path. A parabolic path, this is kinematics from physics. We have 1/2 gt squared, where g stands for the gravitational constant, and that's either going to be -32 feet per second squared or -9.8 meters per second squared. So we have gravity working, then we have initial velocity that's working to change the height and initial height. So we have 3 different things that can change the heights, but they all will model this situation. So the one situation that I have is a ball is thrown down. So if it's thrown down, it should have a negative initial velocity, which it does, from the top of our 220-foot building. So number 1, this tells me my initial height is 220. Number 2, this is in feet, which tells me I'm going to have to look at half of -32, which is -16. So this right here is half of -32. This right here is my initial velocity, which I'm given, and then this is my initial height. What can I do with that? I want to know how long does it take for the ball to fall 108 feet. So a lot of students just like to throw 108 in, and they're like, oh, okay, I'm done. And no, not really. So if the ball falls 108 feet, we have to start at 220, drop 108, we should get 112. And I'm not sure why I just wrote over that in a bad way. So that's where I'm going to set my height equal to 112 and then solve. So I brought everything to one side, then I divided by 2. And I solved this one by the quadratic formula because it looked very complex. And it turns out I have 2 nice answers, 2 and -27/8. -27/8, negative time does not exist. Therefore, it's only going to be at t equals 2 seconds. Which, if I think about it, it's going to look something like this as a graph. It looks something like that as a graph. There is no such thing as negative time. So, then 2 more questions. When does the ball hit the ground? If the ball hits the ground, that hitting the ground means we have a height of 0. So I plug in 0, put this into the quadratic formula, and I get t equals 3.084 seconds. And then the last question, which I hand wrote on here, when is the ball between 112 and 205 seconds? So once again, I redrew this kind of situation and said, okay, ball is going to be on or in between those 2 values, in between these 2 times. We just need to figure out what's this time and what's this time, which we had already solved for the 112 from the previous problem. So we're going to fill in that information. What we have left to do is we have to say, okay, where is the ball at 200? I'm not sure why I put seconds here. What is the ball between 112 and 205 feet? Oops. All right, so we fixed it. And that's going to be from this time to this time. Again, we know this time is 2. You just have to figure out the other time, which is what I'm doing here. When does the height equal 205? I brought everything to one side, factored it completely, and this gives me t equals 1/2. And this is once again negative time, which doesn't exist. So our answers are going to be 1/2 and 2. Hopefully you understood everything, and I hope you guys have a great day. Bye.